Good evening, everyone. My name is Jyoti Sharma, and this is week 6. So, we will cover here the radioactivity. Sh- we will cover some question on radioactivity, and this radioactivity will have like what do you mean by radioactivity? Then, which of the element you can consider that these elements are radioactive in nature? The use of radioactive element. For example, we can estimate the age of any wooden log or let's say any dead body based on this radioactive element concept. So we will talk about this and some basic questions. So let's have these MCQ questions. Okay, my first question is based on how you will consider that this element is radioactive or not. So there is a blur definition, and based on that only I have this question. And this question is, which of the following statement is true regarding element with an atomic number greater than 83? So we have four options here. The first is they are all stable and non-radioactive. B is they are mostly radioactive and undergo decay. C is they exist only in artificial form, not in nature. And D, they are all noble gases. So you have to tell me, if our atomic number is greater than 83, then what is that? What it is deciphering to us? Okay, so very obvious because we are talking about radioactivity. So my answer will be B only. So they are mostly radioactive and undergo decay. So let me tell you why. What is happening is that when you have equal number of neutron and proton, then this will not give you the radioactivity. But whenever your proton is lesser in number as comparison to the neutron, so neutrons are larger in number, proton is smaller in number, then what will happen? The nuclei of your atom will be unstable. Okay, and after it being unstable, it will emit some radiation. That's why this is giving you the radioactivity. So the thing is, if your atomic number is greater than 83, then that atom will be considered as the radioactive, and that atom will undergo into decay, right? So just keep in mind, atomic number more than 83 means that atom will be radioactive in nature. I have explanation for this. So element with atomic number greater than 83, like uranium, plutonium, thorium, are radioactive and undergo spontaneous nuclear decay. Okay, because the nuclei is very unstable in nature. The proton is lesser than the neutron. Neutrons are higher in number, so there will be a disbalance, or you can say the nuclei will be unstable, and because of that, the atomic number that having atomic number greater than 83 will give you the instability in the nuclei, and that's why that atom will be considered as radioactive in nature. And the atom that have the atomic number 83 is bismuth, and this bismuth is the heaviest stable element. But after that, whatever element you will have, that will show some radioactive nature, right? While element beyond it are unstable. So I think this question is clear. Okay, then there is a question on like how this radioactivity was discovered. So there is one scientist, Henry Becquerel. So he accidentally discovered radioactivity when he observed that a photographic plate was blackened by uranium salt. What was the key observation that led to this discovery? So I have four options. Uranium salt emitted radiation only after exposure to sunlight. B is the photographic plate remained unchanged in the absence of sunlight. C is uranium salt blackened the photographic plate even without sunlight exposure. And D is the metal sheets completely blocked all radiation from reaching the plate. So it was kind of experiment that Henry was doing, and it was very accidentally that the result of that experiment reached to the point of radioactivity? So, can you tell me which would be the right answer? Okay, so let me tell you the right answer. So this is C. That is the uranium salt blackened the photographic plate even without the sunlight exposure. So what was that experiment is, so Henry thought that if we will have some element, and uh, if we are covering this element with something from by aluminium sheet, and if we are blocking the sunlight, so what will happen, until the sunlight will give the rays to that element, the element will not emit the radiation. Okay, but what he did is he kept this element in the dark area and wrapped with the photographic plate. Okay, but what happened, because that uranium salt was radioactive in nature, and that's why it spontaneously emitted the radiation. It means the sunlight was not needed at that time, but uranium salt itself emitted the radiation. So that was the accidental discovery of the radioactivity. Radioactivity means spontaneously emitting the radiation from your element itself without the need of sunlight. So this is how this radioactivity was discovered accidentally by Henry. And here, because the radiation has been emitted from the uranium salt, so uranium salt blackened the photographic plate even without sunlight exposure. So I think this is clear. Now let's come to the next question. Okay, if we are converting neutron to proton, so what will how we can represent it? So which of the following correctly represents the conversion of neutron into a proton? And our options are neutron plus electron will give proton. Then neutron will give proton plus positron plus neutrino. And C is a neutron will give proton plus electron plus neutrino, and D is proton will give neutron plus electron plus antineutrino. Ipshmita gave me answer A. Okay, but uh, not exactly, because Ipshmita, electron, if we have neutron, right? If we have neutron, then neutron means no charge, right? So no charge means it will give you the positive charge as well as the negative charge and some other energy, right? And that will not have much mass. So such kind of things will be given by the neutron itself. So so this is the right answer, C. Let me tell you why. So if you have a neutron, neutron means I think I'm not able to write. Let me see the pen. So if you have a neutron, so neutron is presented by this one, right? And this neutron, because there is no any charge, so that's why it has to give one positive charge, one negative charge. And if we have the negative charge, so this is nothing but this is minus beta decay, right? If we have the negative charge, then this will give us the neutrino, and this neutrino is showing us this V. But if you have this positive charge, in spite of this beta, beta in negative, if it is giving you the beta positive, then this will give you the antineutrino, right? So based on that, this is the right explanation, that neutron is giving you the proton, means plus charge, and this is negative charge. So this is how it is balancing no charge on neutron and plus neutrino. Okay, so C is the right answer. And let me show you explanation here. So if you have neutron, this will give you the proton plus electron plus neutrino. And if it is if you will see here, this is the beta minus decay. So if we have the beta minus decay, this will give us the neutrino, right? And just see the explanation of the neutrino. Neutrino is emitted in this process. Neutrino has no electric charge and very little mass. It is fundamental particle that carries away energy and momentum in the decay process, helping to balance the equation. So that's why the answer will be C only, right? I have another to show you the role of antineutrino. So how this antineutrino can help? uh, so if we have the positive, so this is known as the a positive decay, right? And beta plus decay. And if we have the beta plus decay, then this will give you the antineutrino. And this will be happen only when proton will be changed into neutron and positron plus antineutrino. So this is how we can see how proton is changing into neutron, neutron is changing into proton, and how this is giving you more species, right? I'm not able to see. Okay, my next question is, which of the following statement about different type of radiation? So we have three type of radiation, alpha, beta, and gamma. So you have to tell me which one is the correct statement. So, okay, I already have given you the answer. But anyway, so we have four option. Alpha particle have high penetrating power and can pass through, I think something is happening, like I'm not able to see. Okay, yes, it is. Okay, now it is working. So actually, you right now know the answer of this. But thing is, you have to know the difference between alpha, beta, and gamma. So just keep in mind that the gamma has a very intensive power, right? So gamma has a very intensive power, so that's why it has very high penetrating power, right? But if you know the alpha, alpha is nothing but the helium, right? Helium has a two atomic number and four atomic mass, so it means it has some mass, and it also have some charge. This is highly positive charge, so this will give you the high ionizing power in alpha, right? But a very low ionizing power in gamma. So that's why this answer is right, because gamma has high penetrating power, because the energy that gamma rays have is highest as comparison to alpha and beta. But the ionizing power is highest in alpha as comparison to beta and gamma. And because it has the highest penetrating energy, then it can travel more without being distracted. So it travels at the speed of light, right? Okay, so here we have the explanation. If we have beta particle, then these are identical to the helium nuclei, and this also have the high ionizing power, weak penetrating power, right? If we have the beta particle, these are identical to the electron, have medium penetrating power and weaker in ionizing power. But if you have the gamma rays, these have the highest penetrating power and low ionizing power as comparison to alpha and beta. And this is how the answer we defended, right? Okay, so let's come to the next question. Okay, the next question is, which of the following statement is correct regarding isotopes, isobar, and isotones? So you must know the difference between isotope, isobar, and isotone. Based on that, you have the question, and we have four options, right? So first option is isotopes have same number of neutron but different atomic number. B is isobar has the same mass number but different atomic number and chemical properties. C is isotones have same atomic number but different mass number. And D is isotope and isobar have same chemical species. So can you give me the answer for this? Anyone? Okay, so you are confused between A and B. But if I tell you like the options are not among A and D, but something else, it is B. Okay, let me show you the difference between this, right? So uh, if you have isotope means same element. You have same element. You have hydrogen, right? Hydrogen, hydrogen, hydrogen. And if we have same element with same atomic number, so here we have let me change my color. So here the atomic number is 1, 1, and 1, right? So we have same element, same atomic number, but different atomic mass. So here atomic mass is 1, 2, 3, and they have similar chemical properties. So these are known as the isotopes, right? So isotopes are nothing, same element with same atomic number but different atomic mass. Then if we are comparing this isobar, just see the example of this isobar. We have different element, right? We have different element, but the atomic number is same. Atomic number is atomic mass is same and atomic number is different. So just see here, with same mass number but different atomic number, meaning different number of proton and thus different element. So they have different chemical properties. So these are known as the isobar, right? And if we are talking about the isotone, then they have same number of neutron. Okay, so for example, we have silica, we have phosphorus, and we have sulfur, right? And these are our number of protons, because the number of protons are is equal to your atomic number that are denoted as the Z, right? And this 30, 31, and 32 are your atomic mass. And you know that atomic mass is equal to Z plus neutron, right? So if you will calculate and this neutron will be nothing but neutron is equal to your atomic mass minus proton or your atomic number. So what you will do, 30 minus 14, this is giving you 16, and this 16 is nothing but the neutron, right? 51 minus 15, 31 minus 15, this is also giving us 16. And this 32 minus 16, this is also giving me 16. So this is how, if we have same number of neutron but different atomic number, so these are known as the neutron, right? Mm. So I think right now you can give me the answer for this, that isobars have the same mass number but different atomic number and chemical property. So I think from this it is clear. Okay, the next question is, what is the relationship between the average life and the half life of the radiative species? So we have four options. T, here T is nothing but average time. So average time is equal to half of is equal to half life. So this is not, this will not be in option. Then T is equal to half life upon 2. Then C is equal to in C option, T is equal to 1.44 into multiply by half life, and D is equal D option is T is equal to half life multiply by 0.693. uh, yes, Smita, C is the right answer. And how C is right answer? Let's see. So we know that average life. So if it is T, then this is denoted by 1 by alpha, right? So this is one equation. So T is equal to 1 by alpha, or another symbol you can say. And then here half life. This half life is nothing but 0.693 upon alpha. And if we will put together into one equation, then we will get, then T, that is the average life, is equal to half life upon 0.693, and this will be equal to 1.44 multiplied by half life. So it means average life is approximately 1.44 times the half life. So this is how we can solve this question. Now let's come to next question. Okay, this is a numerical question, and I have shown you this. But anyway, so what is the approximate rate of disintegration? And this disintegration rate is also known as activity of a 0.004 gram sample of thorium uh, 232. If its lifetime, half life is 1.4 into 10 raised to power 10 year, then you have to tell me the approximate rate of disintegration. And I don't think that you people can calculate it like very frequently, because like I can't wait much, like I can't give you time to solve this. So I just have to tell you concept very rapidly, and then we will go to the next question. So rate of disintegration means your element is changing, your element is decaying, right? Your element is disintegrated with the time. So how we can write this? Change in change in the concentration of your element, so this is Dn, per change in time, so this is nothing but the rate of disintegration, right? And if we know, we already know that this is nothing but equal to Rn. So this is the first order reaction. If you people remember, the change in concentration of any element per change in time is equal to Rn, and this R is nothing but the constant. This is constant value, a rate constant, and this N is nothing but your original element concentration. Okay, so and why this is first order reaction is that because your rate of disintegration is directly proportional to the concentration of your element, okay, or concentration of your sample. So that's why this is the first order reaction. So this is now very simple. You need to calculate the rate of disintegration. So you need to calculate this dn upon dt. And what has been given is you have sample, and that sample is 0.004 gram, and you have the life, half life. Okay, and the one formula we know that our half life is nothing. Half life is 1 by 2. This is nothing but 0.693 upon alpha, and this alpha is nothing but R. So these are same, right? So from here, if you have half life, then from half life you can calculate this constant. And if you know the constant, and your concentration is also given, that is 0.004 gram, and based on that you can, but just keep in mind this is the rate of disintegration, so we are talking everything in number of atoms. Okay, the number of atoms that has been decay. So half life is half number of atom has been decay, but here the sample is in gram, right? So this is 0.004 grams. So first what we have to do is we have to convert this gram into number of atoms, and then if we already have calculated this r, then we have to put this value r at n, and this will give you the rate of disintegration. So this is how we can calculate this. Let me show you the answer for this. This will be b, and as I told you, we have one thing, that the we have decay constant. This decay constant is 0.693 upon half life, and this is how we can and half life is already given, right? So half life is given in your question only. So this is how you can calculate the decay constant. So this is your decay constant. Now if I go to next one, then you have to calculate, as I told you, we have in grams, but we want the number of atoms, right? Then what we have to do is we have to multiply it with the Avogadro number, then the gram, and then this is the atomic mass, or atomic mass, right? So this atomic mass is 232 of the theorem, right? And this is mass. So mass upon given mass upon molar mass and multiply by Avogadro number, this will give you the number of atoms. So if you have number of atoms, and I already told you dn upon dt is giving you the rn, or alpha n, and that's why. And this rate of disintegration dn upon dt is also known as activity. So this is equal to alpha n. Alpha we have calculated, and number of atoms we already have calculated based on the weight. And this is how we can calculate the activity or the rate of disintegration. And just see, because it is the rate, then this is the unit are atoms per minute decay, right? So per minute this much atoms are decaying. Okay, so this is how we can calculate the rate of disintegration. So I think this is clear. We should move to the next question. Okay, the next question is, when a radioactive element undergoes the emission of two alpha particle followed by one beta particle, the resulting element is a, and I have four options: isomer, isotone, isotope, and isobar. So you have to tell me the right answer for this. Let me show. Okay, so the thing is, if you have some element, that element is A, and this is giving you what it is giving you. It is giving you helium. Like helium, alpha particle is helium, right? So this is giving you helium, and that helium is 2 4, right? But it is giving you 2, right? And then this will give you one element, that is B, and followed by one beta particle. So this will give you beta particle. So beta is nothing but electron, right? So this is giving you one electron, and this is giving you C element. So you have to tell, we have A and we have C. So what is the relation between this A and C? Either they isomer or isotone or isotope or isobar. So this is how you have to tell me, right? So let's see. So this will be isobar. Let me tell you. And isobar we already have discussed. So isobar means you have the same atomic mass. So let's say atomic mass here is X, then this will also be X. But here the number can change. For example, here the atomic number initial was let's say 11, then it may be something else, like it may be 13. So and let me show you the explanation for this, why we have the isobar. uh, okay, so we have okay, so we have two alpha particle means uh, uh, two proton and two neutron, or we can say because it has two proton, and you know, proton plus neutron is giving you the atomic mass, right? And that's why this is 4. So here, if we have some element, so if there was A and this A is giving you B plus uh, 2 alpha particle, right? 2 alpha particle. So this 2 alpha particle means this B has to decrease its atomic mass, atomic number, you can say, by 8. Okay, because here I told you the helium atomic mass is 4 and we have 2 alpha particle, means 8 atomic mass or atomic number you have to reduce from B, because it has been transferred into 2 alpha particle, right? And the atomic number we have to decrease by 4, because this is helium 2 and we have 2 alpha particle, then 4. So this is how new atomic number will be Z minus 4, and new atomic new mass number will be A minus 8. So this is our atomic number, initial atomic number, and this was our initial mass number. And newer one will be Z minus 4 and A minus 8. Okay, and then we have the beta particle emission also. So beta particle emission means this will increase our atomic number by 1. Okay, so right now we had Z minus 4 from here, and if we have the beta particle emission, then this will increase our atomic number by 1. So this will be Z minus 3, and final atomic mass number will be A minus 8. So this is same, right? These are same. So our atomic mass number is same, but atomic number is differing. So that's why we can tell that this is isobar, right? And we already have seen the difference between these. So isomer have same atomic number and also have same mass number, but different energy state. And we right now in radioactivity, we are not talking about isomer at all. And isobar have the same neutron number. Isotope have same atomic number but different atomic mass number, and isobar have same atomic mass number but different atomic number. So this is the correct statement. Now, next come to the next question. Okay, so the radioactivity of a sample is R1 at time T1 and R2 at time T2. So we have radioactivity R1 and R2 and at time T1 and T2. And if the half-life of the substance is T, the number of atoms that have disintegrated during the time interval T2 minus T1 is proportional to what? So we have option R1 minus R2 multiplied by T and divided by T2 minus T1. The B option is R1 minus R2 multiplied by T. C option is R1 minus R2 divided by T2 minus T1. And D option is R1 T1 minus R2 T2. So what do you think? What is the right answer for this? Okay, so let me show you here. The answer is R1 minus R2 multiplied by T. And let's look at the derivation, like why this R1 minus R2 multiplied T will be the number of atoms that has been disintegrated. So let's see the derivation of this. So we know that if we do have the exponential decay rate, or we can say the first order decay rate, then this will be nothing but the concentration that has been left, your initial concentration and e is the exponential minus raised to power minus alpha t, and this alpha is nothing but the decay constant, and this t is the time. Okay, so this is the exponential decay law, or you can say the first order equation. And node is equal to initial rate, initial number of atomic radioactive number. T is the number of atoms remaining at time t, and this is decay constant. And we also know that this alpha is equal to 0.693 upon half lifetime. So this is upon t. And if we know that activity, we also shown in the last question only, that the rate of disintegration is also known as activity, and this activity is nothing but dn upon dt, and this dn upon dt is equal to alpha n. And because we have two time t1 and t2, so here r1 and r2 will be alpha n1 and alpha n2. Okay, so these are the disintegrate rate at T1 and T2, right? So just keep in mind, right now we have two equations here. Then what we will do, the number of disintegration atom during time T2 minus T1, because this was in question. We need to know the number of disintegration during time interval, that is T2 minus T1. This will be nothing but here n decade will be n1 minus n2, and we will because we have r1 is equal to alpha n1 and r2 is equal to alpha n2, and if we will put here, this will be the equation. And again, if we are putting the alpha value into this, then this will be the final thing. So number of atom disintegrated is proportional to the difference in activity. This activity is nothing but the rate of disintegration and multiply by t, and this t is nothing but half-life. So that's how this will give you the right answer. I think it is clear. Okay, next question. This is very much similar to the last question only, but what we did is we changed this alpha with t. So initially our question had a half life, but here we have the decay constant, that is alpha. So the question is, the radioactivity of a sample is R1 at time T1 and R2 at time T2. If the decay constant of the substance is alpha, the number of atoms that have disintegrated during the time interval T2 minus T1 is proportional to what? So here, like in last question, we had the relation with half-life, and here this question is based on decay constant. Very rightly you can say, because we know that our half-life 1 by 2 is equal to nothing but 0.693 upon your decay constant. And in last question, if I show you, in last question, we had this half-life. This was in multiplication, but the equation also said that half-life is equal to 0.693 upon alpha. So I think based on that, you can tell me the right answer for this question. So what will be the right answer for this? So the right answer will be, so right answer will be R1 minus R2 divided by alpha, because the relation is very simple. This is inversely proportional. So that's why in first question it was multiplied by t, but here because the relationship is inverse, so we have to divide it by alpha. And I also have the explanation for this as well, so you can see here. Again, we have the number of radioactive atoms, and this rate is known as activity, and this is also equal to alpha n. We have r1, this is nothing but alpha n1, r2 is equal to alpha n2, and then what we have to do is n decay is equal to n1 minus n2. Then we have to put the value of this n1 n2 into this, and that's how we will get the answer, right? Very simple question. I don't think right now. Okay, the next question is, oh, my screen is little bigger, I don't know why. Okay, next question is, Geiger-Muller counter is primarily used for what? Measuring radioactive emission. B is determining molecular weight. C is analyzing infrared spectra, and D is producing nuclear reaction. So what do you think? What will be the right answer for this? Okay, so here the answer is because we people are talking about radioactivity only. So this method is used to determine the radioactive emission, and that's why A is the right answer. I also have the explanation for this. So this is an instrument designed to detect and measure ionizing radiation, and so this ionizing radiation can be alpha, can be beta, and can be gamma, and the principle is also given here. So we do have the radiation interaction here. So what we will have, we have a chamber, the gas filled chamber, in which we have the ionizing radiation, and this will give you positive ion and as well as the free electrons. And if we will have the voltage and the electron accelerator, then this will give you more free electron, and that will accelerate toward the anode. And this is how, like, this is the basic principle, you can read anywhere. And this is giving you the this will tell you whether your element is radioactive or not, and how much radioactivity it has, right? So I'm not going into detail about this, but you can read. The next question is, the rate of radioactive disintegration of an element is not affected by which of the following condition? We have four options. First is temperature and pressure. B is chemical reaction. C is external physical condition like vacuum, and D is all of the above. So what do you think? What is the right answer for this? Rate of radioactive disintegration of an element. So the right answer is D, that is all of above. Means nothing. It is not temperature and pressure. It is not the chemical reaction. It is not any external physical condition like vacuum will affect the radioactive disintegration, because this is this is the work of nuclei only. Okay, nuclei is only have that energy, and that's why these all factor will not affect this radioactive disintegration, right? I also have explanation for this. So if we have this exponential decay law, and this is nothing but n is equal to n naught e minus raised to power minus alpha t. And if we will see here, this decay constant depend only on nuclear property. External factors do not influence radioactive disintegration, and that's why D was the right answer. Okay. Now coming to the next question. I don't think that I need to explain each of this. Okay. Now you have two radioactive nuclei, X and Y, and here X is an alpha emitter and Y is a beta emitter. Okay, emitter means it is giving you helium, right? So helium is a 2 atomic number and 4 atomic mass. So if Y is giving you, let's say, product A, so this A will have atomic number decreased by 2 and atomic mass decreased by 4. Okay, and we also have one another radioactive nuclei, that is Y, and this is beta emitter. Beta emitter means it will give you product, let's say B, and this product have a number of proton or the atomic number increased by 1. Okay, their disintegration constant are in ratio 2:5. What should be the initial number of atoms ratio of X and Y at time is equal to 0, so that the probability of emitting alpha and beta particles are same at t is equal to 0. So if they are asking, if they are telling us that the probability are same means there is equilibrium condition. So equilibrium condition is, you can say, if you have activity, that activity A and activity B, so this activity will be equal to each other. So that's how we can define this equilibrium condition. So let me show you the answer for this. The answer will be 5:2. So this will be inverse to whatever ratio we had. So initially we had the ratio 2:5, but this will give you the ratio 5:2. So let me show you how. So initially you had this ratio, and this ratio of the disintegration constant, that was the 2:5. Okay, and we need to, and the goal is to find the initial number of atom ratio, and so that the rate of alpha and beta emissions are equal at t is equal to 0. So what we have to do is, as I told you, if it is the equilibrium condition, then the activity will be same for both of the condition. So alpha x and x is equal to alpha y and y. And if we are putting this, nx upon ny is equal to alpha y upon alpha x is equal to 5/2. So this is the inverse of the ratio. So that's how here answer 5:2 will be right one. Okay, this is very simple question, and I think you people should give me the answer for this. So you have four reaction, and P, Q, R, S, and T. You have to tell me because these represent unknown values. And you have to tell me the value for this P, Q, R, S, and T. So A answered, B answered, C answered, and D answered. I think you people can give me the answer for this. So, okay, if you here see, uh, this was 239, right? And it is changing 235. So 235 means it is reducing by 4. So reducing by 4 means it must be alpha particle that has been emitted. So if it is the alpha particle, then alpha particle means helium. So if helium is coming out of this uranium, and this is 4 and 2, it means that this number 239 to 235, this will be reduced by -4. And this should be reduced by -2, right? So here we have P is equal to 90. So this can be this one and this one as well. Okay, then come to the next thing. You have 233 and this is also 233. 233 means it can be either your electron that has been emitted, or it can be a neutron, right? But because we are talking about alpha, beta, and gamma, then this should be beta, right? So beta means if we have beta, so this should be increased by 1. This should be increased by 1. Okay, so it was 90, then it would be 91. So okay, this these two also have this 91 and 91. Now coming to the next, again it is 235 to 231, means minus 4. So if it is minus 4, means alpha particle has been emitted. So alpha particle has been emitted means the two atomic number should be reduced. So initially it was 91, then this should be 89. 91 minus 2, then this should give us 89, right? So again, we have both options are right. Then, and this T is what? So we have talked about this T was alpha, this T was beta, and this T was again alpha. Okay. So this is how you can tell the answer. So this will be A, because like this first T was alpha, this second T was beta, and this third T was again alpha. And this is how this one is more accurate answer. So A is the right answer. Um, Again, here you can see first it was like this, then if it is alpha particle, then we have 2, and here we have 4. Then this has to reduce or decrease the mass number by 4 and atomic number by 2, and that's why your atomic number will be 90 and your atomic mass will be 235. Then this will be beta, and because of that beta, your atomic number will be increased by 1. So from 90 to 1, so this will be 91, and your atomic mass will be same. This is 235. Then third, again it was alpha. Then again your atomic number will be reduced by 2, atomic mass will be reduced by 4, and this is how this will be 89 and 31, right? And this is how you can give the right answer. Okay, we have two scientists, and these two scientists are Curie and Joliot. So these people were credited with the discovery of what? So you have to give me the answer for this. The first option is X-ray. The second option is natural radioactivity. The third option is artificial radioactivity, and D is nuclear fission. You can write in the chat box as well, or you can even speak. What do you think? What is the answer? So this Curie and Joliot discovered what? Not D, but they discovered artificial radioactivity. So C is the right answer actually. And so what they did is we have polonium and radium, right? So if we have the polonium, and if we are inducing if we are striking this element with with the neutron, this is 0 and 1, then this will give you the decaying product. Okay, and so they used a lot of elements, and for example cobalt and radium. So, and that's how they discovered that the element that we do not have right now naturally, but we can have some element that are radioactive in nature, and we can utilize them for a medical purpose and for a lot of purposes, right? So they discovered this artificial radioactivity. So C is the right answer. Maybe I have little explanation for this. So radioactivity was first observed by Curie and Joliot. They observed that when certain stable element, for example, aluminium, were bombarded with alpha particle, they become radioactive and they will emit beta particle in this process. Uh, and this was groundbreaking discovery, because before to it, all non-radioactive elements were naturally occurring, and so that's why this like C is the right answer. Okay, if you people know that radioactive elements are used to calculate the age of any dead organism, any wood, or any organic matter, right? So how older that organic thing is, we right now we have. So this is very important application of radioactive material, and we exploited the ratio of carbon 14 and carbon 12. Okay, so based on the ratio carbon 14 and carbon 12, we can estimate the age of any organic thing. For example, wood, for example, uh, dead animal, right? So based on that, we have question. So if we have that ratio of carbon 14 to carbon 12, just keep in mind carbon 14 is radioactive in nature and carbon 12 is not radioactive. Okay, and if that ratio is given, is 25% of that found in the atmosphere. Okay, then you have to calculate the approximate age of that artifact, and half life of your radioactive carbon, that is C14, is given, and that is 5730 year. So this is very important, and this is very interesting question, that if you know the half life and if you know the ratio of C14 and C12, then you can estimate the age of that organic matter. So how we can do this? Do you have any idea about this? Okay, so the basic thing is that, uh, okay, so initially we have carbon, and this carbon has that atomic number 12. Okay, but we have some energy that we get from the sun. If we have that energy from sun, what this energy will do, this energy will change that C12 to C14. Okay, so basically in atmosphere we have C12, but after some rays that will strike to C12, that C12 will be changed into C14. And you can also say that we have the nitrogen as well, and if it this sun rays will strike to the nitrogen, it will give you the C14. So we have some ratio of C12 and C14 in the atmosphere, and that ratio is approximately 10 raised to power minus 12. So what does it mean is that for 12 number of atoms of C12, we have one atom of C14 in our atmosphere. Okay, then what will happen? This carbon will change into CO2, right? Then in our body, in any organic body, we will have, it may be this CO2 may be composed of this C12 and may also be composed of this C14. Until we are living, that proportion will be constant as the proportion that we have in the atmosphere, that is 10 raised to power minus 12. But if some organism dies, then what will happen? This will reduce the amount of this C14, and this will start decaying because this is radioactive in nature. That means if some body has been died, then the ratio of this C14 to C12 will reduce, because this radioactive C14 will start to decay, and this ratio will be reduced. So based on that reduced ratio, we can calculate the age. So let's see how we can calculate this. So this was the basic principle. So again, I have first order decay law, and that is equal to n is equal to n node e raised to power minus alpha t, right? And from here we can calculate the time t. So this is the age of any of your organism. Okay, then this n node is equal to initial ratio. So initial ratio was 100%. Then your current ratio is 25%. Okay, and then we have the decay constant. From that decay constant you can calculate, and half life is already given, so from that half life you can calculate the decay constant. And if you have decay constant, that you can put that decay constant into this, and you have the value of this n node. This n node is nothing but 100, and this n is nothing but 25. And so this is how you can calculate the t. Let me show you how. So we have 100 upon 25, and this is how we calculated the time t, that is the average time. So average time of the wood is 11620 years. Okay, so this is how we can calculate the age of any artifact. I think this is clear how we exploited the radioactive C14 and C12 ratio to calculate the age of any artifact. And based on that, the scientist who discovered this radioactive dating, this is also known as radioactive dating, and that scientist got the Nobel Prize for this, because a lot of fossil fuel, like the age of that fossil fuel were unknown, and based on this methodology, or based on this technique, a lot of like fossil fuel age has been known. Okay, and that's why they got the Nobel Prize. Okay, the next question is, if we have the uranium, atomic number is 92, atomic mass is 232, and this is alpha emitter with half life is 4.468 into 10 raised to power 9 year. And if we have a 0.750 gram sample of uranium 238, then you have to tell me approximately how many alpha particle will it emit per second. You just have to keep in mind, one atom will emit one alpha particle. Okay, so what you have to estimate is, you have to estimate the number of atoms that we have. Okay, and based on that we can calculate the alpha particle that it will emit per second, right? And if you will see here, the half life is in years. Okay, and we need here per second. So first you have to change this year to second. So you have half life. From this half life we have the relation very like we have repeated this relation, that our decay constant is 0.693 upon half life. So from here we can estimate this half life, sorry, this decay constant, because we already have the half life. If we have the decay constant, then what we can do is we can estimate time t, and other things we can estimate. Okay, based on another formula for this first order decay law. So let's see how we can calculate this. And just see here again, we have gram sample of uranium, but what we need is the number of atoms. So how we will calculate this number of atom? We have the Avogadro number. We have to multiply this Avogadro number to the given mass upon molar mass, and the molar mass is 232. So Avogadro number multiplied by 0.750, that is given mass, upon molar mass. So this will give you the number of atoms of the uranium. Okay, if you have half life, then let's see how we can do this. We have repeated a lot. Now this decay constant is equal to 0.693 upon half life. Based on that, and just keep in mind this is in year, but we need it to seconds, so that's why we multiplied this 365 multiplied 24 multiplied by 60 and 60, so that this year can be changed into second, right? And this is how we calculated the decay constant. If we have the decay constant, then this mass, the number of atoms will be mass of the sample upon molar mass multiplied by Avogadro number, and this is how we calculate the number of atoms of the uranium. Okay, and this is 1.897 multiplied by 10 raised to power 21. And then uh, we need to calculate the number of disintegration per second, and this disintegration activity is also known as the alpha and n, and we already have calculated this one using our half life and this n, the number of atoms, and this is how we can calculate the disintegration per second. And each uranium atom emit one alpha particle, so number of alpha particle emitted per second will be same. That will be 2785 alpha particle per second. So this is how we can calculate this. So I think this is clear. Should we go to further? Okay. A very basic question, and I think you people should give me the answer for this. If you have atomic number Z of an element increase by 1 during a nuclear transformation, what type of decay has occurred? Alpha decay, beta decay, gamma decay, positron decay. If your element number increases by 1, so initially let's say you had element A, and that element had this 5, and let's say here it was 6, and this is giving you B, and this B has 6, and this is 6. So what do you think, what kind of decay has occurred? So this was beta, so beta means, so this will give you beta, so beta is 1 0. So that's why, because of this 1, this has increased by 1, right? So this will be the beta decay. Let me show you the answer for this. Okay, so beta is beta minus, and here if we will see, if we have, let's say, carbon 14 and the atomic number is 6, atomic mass is 14, that will give you the nitrogen that have the atomic number 7, atomic mass 14, and it has been increased by 1 because one beta or electron has been emitted. Okay, and if this will be emitted, this will increase your atomic number by 1. So this is how the beta decay has occurred if your atomic number has been increased by 1. Again, very simple question. If an element undergoes alpha decay, what happens to its atomic number and mass number? We have option Z decreases by 2, A increases by 4. Answer B is Z decreases by 4, A increases by 2. C is Z decreases by 2, A remains the same. And D is Z remains the same, A increased by 4. Very simple question. If you have like element has been undergone by this alpha decay, what do you think? What would be the right answer? We already have talked about such kind of equations. Anyone want to give me the answer for this? Okay, so if it is the alpha particle means helium has been emitted. So helium has 2 atomic number and 4 atomic mass. So if you have another product, that another product has atomic number reduced by 2 and atomic mass reduced by 4, because helium has been emitted, and helium has 2 atomic number and 4 atomic mass. So that's how answer will be A. So Z is atomic number. So atomic number will be reduced by 2, and atomic mass, that is A, and A has been reduced by 4. So this is nothing but you can write here like this. If you have X and this X is giving you Y plus helium. So this is 2 and 4. Okay, so this will be, let's say this was x minus 2, and this will be y minus 4, and this will be x and y. So initially, let's say we had x and y, but helium is giving you 2 and 4. So that's why the product y have the atomic number that will be reduced by 2, and atomic mass that will be reduced by 4. And that's why this A is the right answer. I think this is clear. Okay, so next to the next question. Um, so we already have covered this. So for example, it was 92 and 238, and helium has been emitted. So helium is nothing but the alpha particle. Then this have the 2 and 4. So that's why this will be 90, 92 minus 2, and this will be 234, 238 minus 4. So this is how you can tell if alpha particle has been emitted. So what will be the atomic number and atomic mass for your product? Okay, so which statement is true about gamma decay? It changes the atomic number but not the atomic mass number. It changes the mass number but not the atomic number. It does not change either the atomic number or mass number. It increases the atomic number by 1. So what do you think? What is which statement is true about gamma decay? So gamma is like radioactive, sorry, this is just like electromagnetic radiation, and if it is the electromagnetic radiation, it means it doesn't have the mass, and it doesn't have any ionizing power, right? Very low ionizing power. So that's why this will not have any mass and even any number. So that's how this will give you the answer, that is C, that it does not change either the atomic number or atomic mass. So let me show you. If you have here A and this have X and Y, and if some gamma rays gamma has been emitted, and this is giving you the product, but this product will also have X and Y same, but this will give you the gamma radiations or gamma decay element. So that's how your atomic number and atom mass number will be same. So that's why C is the right answer for this. So let me show you. So if you have the cobalt, and cobalt has atomic number 27, atomic mass is 60, then this will give you again the cobalt, but your gamma will be released. So gamma is like some energy, electromagnetic radiation, and this will not change your atomic number and atomic mass. So no proton, no electron are lost. So Z and A remains the same here. So I think this is clear. Now coming to the next question. Okay, we talked about alpha particle, we talked about gamma, and this question is based on the positron. So if you have element and that element emits the positron, what happens to its atomic number? So Z decreases by 1, increases by 1, Z remains the same, and Z decreases by 2. If element emits a positron. Positron is like opposite to electron. So as I told you, electron will increase the atomic number by 1. Okay, so this will reduce the atomic number by 1. So this is how. So this atomic number is denoted by Z. So Z will be decreased by 1. If it is increased by 1, then this will not be the positron, but this will be the beta particle, or you can say this is electron. But if it is positron, then your atomic number will be reduced by 1. So this is something proton. Right, so here you can see if you have carbon, and this carbon have atomic number 6 and atomic mass 11. So this will give you B, boron, and have the atomic number 5, and atomic mass will be same because positron has been released. So here if you will see, the number has been reduced by 1. Okay, which of the following is radioactive? Very simple question. A is carbon 13, oxygen 16, sulfur 35, and neon 20. You can write in the chat box answer A, B, C, D, or which answer you think is right. Which of the following is radioactive or radioisotope? Carbon 13, oxygen 16, sulfur 35, and neon 20. Neon is the inert gas, right? So neon will not be the answer. And we have talked about carbon 14 is the radioactive or radioisotope and not the carbon 13. So this will not be the answer. Then oxygen 16, this is very stable isotope, and this is not the radioisotope. And the remaining one is the sulfur 35. Yes, this is radioisotope. Let me show you the answer for this. So C is the right answer, that is sulfur 35. And if we will see, so if we have sulfur, that is 16 and 35, and this will be decay and will undergoes a beta decay. So this will release beta. So beta means your atomic number will be increased by 1. Okay, so this will give you the chlorine that have the atomic number 17 and atomic mass 35, very much same or similar. So this is nothing but the big beta decay, and if it is undergoing with beta decay, then this is radioisotope, right? So this is making you this sulfur is making the correct answer. Is it clear? So let me. Okay, so we have four isotope of carbon, and you have to tell me which one is the radioisotope of carbon. So we have carbon 12, 13, 14, and 11. What do you think? What is the radioisotope of carbon? We already have talked about radioactive dating, and in which we had the ratio of C14 to the C12. Yes, yes, answer should be C only. So this is carbon 14. Uh, so if we will see here, carbon 12 and 13 are very much stable. So these are not the radioactive, but this 14 and 11 are unstable. So we can say like these are the radioactive. But this 14 undergoes into beta decay, and this where this neutron transform into proton, and this will also emit the electron, and this is how we can show this decay. And we already have talked about this C14, that this is used in radiocarbon dating. And so the more no doubt 11 is also the answer, but the more appropriate is C14, right? Uh, here also, based on your query, so we have the carbon 11. This has a radioisotope, but it has a very short lifetime, the near to 20 minutes. But not like carbon 14. Carbon 14 had a lifetime near to 5,000 or 6,000, I think 5730 or something like that. So it has very short lifetime, so that's why we the more accurate answer is C14, not C11. So let's come to the next question. Which of the following series is the actinium series? 4n plus 1, 4n, 4n plus 2, 4n plus 3 series. So what do you mean by this 4n plus 4n, 4n plus 2, 4n plus 3? So Ganesh gave me D answer, that is 4n plus 3 series. So these are nothing but this is the atomic mass, or you can say the mass number. So if it is undergoing into some decay, then each of the element have the atomic mass that will be equal to that series. Either it is 4n plus 1. I show you actually. So yes, D is the right answer, and let me show you how. So this is also known as 4n plus 3 series, and it will start from actinium. Okay, and this will include thorium and a lot of elements. And here the sum of 4n plus 3 define the isotope in the series. And let me explain you what do you mean by this. Uh, so for example, you had the uranium, and this uranium had 92 and 235. So if you will see here, if n is equal to 58, okay, so if n is equal to 58, then this is giving you 235. uh, so if you will multiply this 4 into n, so n here is 58, and 4 multiplied by n plus 3, this will give you the 235, and this 235 is your mass number. Okay, and this will be your first isotope in the actinium series. Then you will go to the second one, that is the thorium. So what happened here, the atomic so here n is equal to 57, and if you will see here, atomic mass will be 231, and this 231 is same like this. So likewise you can predict what will be the atomic mass of your next element, right? So this is how this actinium series is nothing but 4n plus 3. And along so if you have another element, if you have n is equal to 56, then again this will give you the 227, and this 227 is atomic mass or mass number. So this pattern continue with each subsequent atomic mass number fitting the formula 2n plus 3, decrease by 4 each time due to emission of alpha particle. So what is happening, that alpha particle has been emitted from that each of that element, and that's why this will reduce by 4 each time. So this is how this actinium series is 4n plus 3, right? Okay, the next question is which radioactive series begin with uranium 238 and follows the decay pattern 4n? And we have option actinium series, thorium series, Neptunian series, and uranium series. Obviously, if it is beginning with the uranium, then it should be uranium series, right? If I'm not incorrect, right? Okay, so this will be the uranium series only. So uranium series also known as the 4n series, and it will start with the uranium and it will ending with lead, that is 206. And this will characterized by the sequence of alpha and beta. In last question we had the alpha decay, but here there is a sequence of alpha and then beta, alpha and then beta. And the stable isotope will be lead, that is 206, and this will follow 2n pattern. Okay, okay, next question is very easy again. Which of the following series is characterized by 4n plus 1 series and begin with thorium? I think from question only you can estimate like what will be right MCQ. Yes, Sonia, the answer will be C only. because it is started with thorium only. So thorium series follows 4n plus 1, and it will start from thorium. And again, because the end stable isotope is lead, so this will again end with lead, and the atomic mass is 208. Okay. So again, this is the question related to your radiocarbon dating. So if you have some ratio of C14 to C12, then you can estimate the age of any wood. Okay, and this question is again related to your radiocarbon dating. So the question is: a team of archaeologists discover ancient wooden artifact in a burial site. Analysis reveal that only 60% of the original 14C remain in the wood. So initially it was 100% 14 carbon, but because it is radioactive in nature, then only 60% has been remaining here. Okay, and the half life of 14C is given, that is 5730 year, and you need to calculate how old are the artifact. Very much similar question. First, you have half life. Based on that half life, you will calculate the decay constant. If you have decay constant, and you know initially we had 100%, right now you have just 60%, then we have first order reaction, that is n is equal to n node e raised to power minus delta t, and delta we already have calculated, that is the decay constant. And we know this is 60%, and node is equal to 100%. Initially it was 100%, and we need to calculate t only. So this is how we can solve this question. Very simple. So let me show you how we can do this. So this is our first equation, and t is equal to n node e raised to power minus delta t. This is the amount that has been remained. So remained amount is 60%. N node is equal to initial. So initial was 100%. So if we will calculate NT upon N node, so this will be 100 upon 60. Sorry, NT is 60, N node is equal to 100. So 60 upon 100, this will give you 0.60. Okay, and half life is already given. So based on your like this equation, decay constant is equal to 0.693 upon half life. You can calculate the decay constant. So we already have calculated this decay constant. Then we put this decay constant into this one. And we have this nt, we have n node, we have calculated this. So we need to calculate just the time of the artifact or the age of the artifact. So this is how we can calculate. Let me show you. So we have calculated this n upon n node. This was 0.60 is equal to e raised to power delta t, and this is how we can calculate the t, and this t will be 4234 years. Okay, so this is how based on this radiocarbon dating, we can estimate the death of the organism and from where the carbon 14 has been started to decay. Okay, this is again very much similar question. So what we have initial mass of the iodine isotope, and it was 50 gram, and determine the approximate iodine mass after 45 days if the half life of the isotope is 12 days. So first, what you have half life. So based on that half life, just calculate the decay constant, because the half life is equal to 0.693 upon decay constant. So from here you can calculate the decay constant. Okay, then initially you had the mass 500 gram, but you need to calculate what will be the remaining mass after 45 days. So t is already given, so you need to calculate n. Okay, and n node is equal to 500 gram. So we know the equation, n is equal to n node e raised to power minus delta t. Decay constant we have calculated, t here is 45, n node is 500 gram, and you need to calculate n after time t. So time t is 45 days. So this is how you can calculate um, the approximate iodine mass after 45 days. And let me show you how you can calculate this. So okay, so we have that equation, n is equal to n naught e raised to power minus delta t, and we have the half life. Based on that half life, you calculated the rate constant. So the rate constant is now 0.05775 per day, and you can see the unit of this rate constant. If it is per day or per time, it means this is the first order reaction, right? And this equation, that n is equal to n node e raised to power minus delta t, this is the first order uh, decay equation, right? Then what we will do, n node is equal to 500 gram, t is equal to 45. You just need to put them into the equation to get n. So if you will calculate n, then this will be 37 gram. So this is very simple question, and this is how you can calculate this. Okay. The next question is, Abhi, you raised your hand. You want to speak something, or you have any query? Then you can write in the chat box. Anyway, so the next question is, if we have two radioactive material, Y1 and Y2, and that have the decay constant of 5 delta, or like, I don't know how you will pronounce this, delta or alpha. So I interchange alpha and delta. So right now I'm pronouncing it with delta. So we have 5 delta and delta respectively. If initially they have the same number of nuclei, after what time will be the ratio of the number of nuclei of Y1 to that of Y2 be e raised to power minus 2? So what you need to do is, you need to calculate the ratio, and the ratio of Y1 divided by Y2. Okay, and how you will calculate this ratio, Y1 upon Y2? We have a very simple equation, that your n is equal to n naught e raised to power minus alpha t, right, or delta t, whatever you say. And if we have that equation for y1, we also have that equation. Y2, we also have that equation, where the decay constant we have 5 delta and delta only. So that two equation we will have, we will divide that two equation, and this is how we will have the ratio of y1 divided by y2. This is how we can, let me show you how we can do this. So first, for material y1, equation will be y1 n is equal to n node e, and here you are changing your constant delta with minus 5 delta. Okay, and t, and likewise you will calculate it for y2. Then we need to and we know that the ratio of this is given, and this ratio is e raised to power minus 2. So we will substitute that into expression, and this is how we will calculate the time. So this time will be equal to 1 by 2 alpha. So I think this is clear. My pen is not working right now, so I'm unable to write anything here. But I think you can like, you already understood what I want to say. So you just need to do is, you have two equation. In that two equation, write the value of your alpha. This alpha will be 5 alpha and alpha, and then the ratio is already given. That ratio is equal to e raised to power minus 2, and then you have to cancel out n node, and then this is how, and even the delta, and this is how you will get and the t value. Okay, this alpha will not be cancelled, so because this will be given in the answer only. So this t is equal to 1 by 2 alpha. Okay, again, very simple question. Which of the following statement about isotope is correct? So I have four options. They have the same number of neutron but different number of proton. B is they have same mass number but different atomic number. C is they have the same atomic number but different atomic mass. D is they have different chemical property but identical physical property. What do you think? What is the right answer for isotope? We are talking about isotope. You can write in the chat box as well. What do you think? What is the right answer for this? Okay, if this is the isotope means your atomic number will be same, but atomic mass will be different, right? So they have same atomic number but different atomic mass. So for example, C14 and C12 are isotope because the atomic number is 6, 6 for carbon, but here atomic mass is 14 and 12. So C14 and C12 are isotope to each other. Or you can say because we have the stable element is C12, so the isotope of C12 is C14 because the atomic number is 6 only, but the atomic mass is changing from 12 to 14. So this is how we can say in the isotope we have the same atomic number but different atomic mass. Is it clear? So isotope are variant of same chemical element that have the same number of proton. And that's why the same atomic number but differ in number of neutron, leading to different mass number. So this difference in neutron count result in varying atomic mass among isotope of the same element. So just keep in mind because you have different number of neutron, so that's why your atomic mass number will be different here. But your atomic number will be same because number of protons are same. Okay, again very same simple question. If you have two isotope of an element have mass number of 35 and 37, the atomic number of element is 17. How many neutrons are present in each isotope? So the answer are 18 and 20, 17 and 19, 20 and 22, 19 and 21. We already have discussed if we have the two isotope means atomic number will be same. Atomic number is 17 for this, and atomic number is nothing but number of protons, right? And we have different mass number here are 35 and 37, and this mass number is the sum of proton and neutron. So if you know the value of proton, you can calculate the neutron. So you can tell me the neutron. Someone gave me answer. Venkat Rao and Chinna is giving me B answer. Let me see. This is A, and let me show you how. So, as I told you, atomic mass minus atomic number will give you the neutron. Okay, so for first you have mass number 35 minus atomic number 17, and this is how the number of neutron is 18 for first isotope. For the second one, atomic mass was 37 and atomic number was same, that was 17, and this is how number of neutron is 20. So we have isotope 18 and 20 respectively. Is there any problem with this? Very basic question. You just need to know that atomic mass or mass number is equal to the sum of proton and neutron. Okay, Sonia. Okay, which pair represent isotope of the same element? So we have carbon 612, oxygen 816, helium 1 2, magnesium 12 24. Which pair represent isotope of the same element? I think my answer is, my question is not fully here. Uh, I think but there is some discrepancy with this question. I think then I should go with another one only. Okay, which of the following isotope have the same number of neutron as 17 chlorine 130 chlorine 35? So you have to tell me like which of the element has same number of neutron as we have in chlorine. And here so you can calculate the neutron in chlorine will be 35 minus 17. So this will be the number of neutron. And from here, like you have option A, B, C, D. What you will do, you will subtract your proton from atomic mass, and your atomic mass is written at the top, your atomic number is at the bottom. So whenever you will subtract it, then you will get the same you will get the number of neutron. So you have to see whether your number of neutron are same as given in the question. So this is how you can tell me the right answer for this. Venkat Rao gave me B answer. So yes, this is B answer, and let me show you how. So number of neutron for chlorine will be 35 minus 17. This will be 18. And if you will calculate for sulfur, 32 minus 16. This is 16. Argon, 36 minus 18. This is 18. This is similar to whatever was in question. Then phosphorus, 31 minus 15 is equal to 16. So these are not the same, but for argon it is same. So we have 18 neutron, right? So this is how we can give the answer for this. So B is the right answer. Again, you have very much similar question, and you have to tell me, we have two isotope for uranium, and here the atomic number is 92 and 92, but atomic mass is 235 and 238. Differ in their number of what? Protons, electron, neutron, proton, and a neutron. So see here, this 92, this 92 is nothing but the number of protons, right? So your proton is same, 92, 92. As we already have discussed, whatever has been written in the top, so this is atomic mass, or you can say the mass number, and this mass number is the sum of proton plus neutron. Okay, and if this is 235 and 238, so atomic mass is different, but your atomic number is same, so means number of proton is same. So what will be the differing? Is what it will be? It will be proton, electron, neutron, or proton and electron. You can tell me right now, based on the difference in your atomic mass. And this atomic mass is nothing but the sum of neutron and proton. And your proton, that is atomic number, is same. So what is differing here? Neutron, right? So this will be neutron. So just see here how we can calculate this neutron. We have to subtract this atomic number from atomic mass. So we have 235 minus 92. So here for the first isotope, the number of neutron will be 143. For the second isotope, this will be 238 minus 92. So this will be 146. So this is how this two isotope is differing by 3 neutron. Okay, so that's why this C answer is the right one, right? Again, same type of question. So we have nitrogen, and this nitrogen have 7, 13, and it decays to form the carbon. So which particle is emitted? So we have electron, alpha particle, neutron, positron. So just see, from 7 to 6. So it has been reduced by one atomic number. And if you will see the atomic mass or mass number, it is constant. Not Praveen, not exactly see. Just see, like if it would be the neutron, then uh, neutron means there is no any charge. Or what I can say is, just keep in mind, your atomic number is equal to number of protons, right? And if in another way, if I will tell you, neutron is like neutron have no charge. But here if we will see, then from 7 to 6, so something is going on, something is going out. So this can't be neutron. This will be positron. Let me show you how. So just see the equation that I have written at the bottom. So here we have nitrogen 713. This will be changed into carbon 6 and 13, and this is giving you the positron. So whenever it will be positron, then your atomic number will be reduced by 1. If it would be electron, then your atomic number should be increased by 1. But if it is a positron, then it should be reduced by 1. And then the antineutrino. So this is how this is beta plus decay. So I think from here it is clear why this is positron. So if it is from 7 to 6, means your atomic number has been reduced by 1, then it should be positron. It is been reduced by 2, then it should be alpha particle. It is increased by 1, then it should be electron. If there will be same 7 and 7, then this should be neutron. Okay, so this is how the D is the right answer. Okay, again we have one numerical question, and this is, after 10 hours, only 0.20 gram of radioactive isotope remain from a initial quantity of 2 gram. What is the approximate half-life of this isotope? So what they are saying, that initially we had 2 gram. Okay, but after time t, after time 10 hours, the isotope, radioisotope has been remained 0.2. So we have n value. So this n value is 0.20. We have anode value. This is 2 gram. And we have time, that is 10 hours. So from here, we can calculate decay constant. If we have calculated decay constant, then we know that we have relation between this decay constant and half-life. That is, half-life is equal to 0.69 upon decay constant. So if we have decay constant, then we can calculate the half-life. Okay, so this is how we can calculate this. So let me show you how we can do this. As I told you, n is equal to n node e raised to power minus alpha t. N node is equal to 2 gram, and n is also given, that is 0.2 gram, and t is equal to 10 gram. So based on that, you can calculate the decay constant. Okay, so as soon as you calculate the decay constant, you can put that decay constant into the third step, from where you can calculate the half-life, and this half-life is equal to 0.693 upon decay constant, and this is how you can calculate the half-life of isotope, and this will be nothing but 3.9 hours. Okay, I think this is clear and very simple question. Okay, so we have some question on application of radioisotope. So you have to tell me which of the following radioisotope is commonly used in medical imaging and thyroid function test. So we have iodine 131, carbon 14, uranium 238, and oxygen 16. So what is the right answer for this? So which radioisotope is used for thyroid function test? Okay. Uh, here, uh, let me show. Okay, so if we go to iodine 131, yes, this is used for thyroid function testing. We already have seen the use of carbon 14. So it will tell you the age of any organic matter. Uranium is the fuel that we use to generate the electricity. It is also used in like atomic bomb and all. And oxygen 16 is a stable isotope. This is not the radioisotope. So the only option that we have is iodine 131. So A answer will be the right one. So if you see here, iodine 131 is the radioisotope, and that emit beta and gamma radiation. And this is used to diagnose and treat thyroid disorders. We already have talked about carbon 14 that is being used in radiocarbon dating, a uranium 238 used in nuclear power generation, and 16 is the stable isotope. Okay. Okay, next question is, which of the following radioisotope is commonly used for the treatment of cancer in radiation therapy? So we have cobalt 60, carbon 14, hydrogen 3, and phosphorus 32. So which of the radioisotope is used for the treatment of cancer? You should know about this. This is very important question. So we already have talked about carbon 14, right? And hydrogen 3 is not the answer. Phosphorus is not the answer, but the cobalt 30, cobalt 60. Sorry. So the right answer is A. If you see here, I have written something. So cobalt 60 is a powerful gamma ray emitter, and this gamma ray emitter is used in radiotherapy to target and destroy cancer cell. As I told you in a very initial question, that gamma ray have high power. So that's why this can be used to target and destroy the cancer cell. And so it is used in device like the gamma knife for non-invasive tumor treatment. And we already have talked about this carbon 14 for radiocarbon dating. This tritium, that is hydrogen 3, is used in self luminous device and nuclear research. Phosphorus 32 is used in biomedical research for DNA labeling, because we know that DNA have phosphorus in the structure of the DNA. So that's why this is used for DNA labeling and all. So the right answer is cobalt 60. Okay, which of the following radioisotope is used in measuring the thickness of material in industry? So the option we have: strontium, carbon, uranium, and potassium. Carbon is not among the right answer, because we have talked about the application of this. Uranium, we already have talked about this. Then among A and D, we have the answer strontium and potassium. So what do you think? What is the right answer? A or D? So the right answer is A, that is strontium. And this is something that you have to remember, not very logical in nature, but yes, the property of strontium are like this, that they can be used to measure the thickness of material in industries. So A is the right answer. So here I have written something. So it will emit beta radiation, which is useful in gauging material thickness in industry like metal rolling and paper production. And we already have talked about this carbon 14 and 238 uranium. But if you will see here potassium 40, then this is naturally occurring isotope in rocks and is not used in industries, right? So the answer will be strontium. Okay, we have last three question, uh, very basic question about nuclear fusion and spallation, because this was the last unit of like week 6. So the last third question is, which of the following correctly describe nuclear fission? So I have four options. Two light nuclei combine to form a heavier nucleus. B is a heavy nuclear split into two or more smaller nuclei. C is a neutron is absorbed by the nucleus but no energy is released. And D is a nucleus breaks apart only due to radioactive decay. So what do you think? What is correct information about nuclear fission? So fission means splitting or breaking, right? Ganesh told that this is option B. Then yes, I will go with option B only. So here, heavy nuclei will split into two or more smaller nuclei. Yes, answer is B only. So in nuclear fission, heavy nuclei, for example, uranium 235, will absorb a neutron and will split into smaller nuclei. So these are known as like fission fragments, and this will release enormous amount of energy, and that's why like this nuclear fission is used in nuclear reactions that will generate your electricity, right? Yes, because that whenever there is a splitting or fragmentation of nuclei, then this will give you enormous energy. Okay, the next question is about nuclear fusion, but not nuclear fission. So, why does nuclear fusion require extremely high temperature? So, we have four options: to increase the mass of the reacting nuclei, to overcome the repulsion between atomic nuclei, to generate neutron needed for the reaction, and D is to slow down the nuclear reaction. So why does nuclear fusion require extremely high temperature? If you know that only experimentally we performed nuclear fission on earth, but it is not possible. We need a very high temperature. So the high energy that we get from the sun is because of the nuclear fusion. So we have uh, hydrogen and hydrogen, and this will fuse together and this will give you the helium. Okay, and this is how, and this will give you the more energy than nuclear fission. So nuclear fusion is giving more energy than nuclear fission, but this is not very much feasible on earth because we need extremely high temperature. If you know the temperature of the sun, approximately the temperature is 5800 Kelvin. So that much temperature we need for the nuclear fission. But why do we need that much higher temperature? Because see now, we have two nuclei, we have two separate nuclei, and these two separate nuclei, for example, hydrogen and hydrogen, and we have to fuse it together. And but you know, two nuclei will repel to each other, so we have to overcome this repulsion to come together. I think she gave me right answer. Okay, so that's why B is the right answer, because you have to fuse two nuclei to each other, and two nuclei will give the repulsion. So we have to overcome this repulsion to fuse these two nuclei, and that's why we need extremely high temperature for nuclear fusion. So see here, nuclei are positively charged and repel each other due to electrostatic force. High temperature given them enough energy to collide with enough force to fuse together, releasing energy. So that's why B is the right answer. Okay, this is last question, I think. What happens in a spallation reaction? So we have a neutron is absorbed by nucleus, making it unstable, and B is a high energy particle strike a nucleus, causing it to eject several smaller particle, and C is two lighter nuclei combined to form heavier nucleus, and D is a nuclear split into two fragment, releasing energy. So Dilip Kumar gave me answer B. Yes. So what will happen if we have high energy particle, and that will strike a nucleus? So a lot of particle will be released. So that's how this is known as the spallation reaction. So that's why the answer is B only. So here, um, so a neutron or proton will bombard a heavy nucleus, for example, lead or tungsten, and it will cause to release multiple smaller particle, mostly neutron and proton. And this process is used for neutron generation in particle accelerators. So that's why the answer B is the right one. Okay, this is last question, I think. Yes, last question. So, what is the primary role of moderator in nuclear reactor? So, to increase the energy of neutron for faster reaction, to slow down neutron, making fission more efficient, to absorb excess neutron and stop the chain reaction, and to cool down the reactor core by removing excess heat. So, the primary role of moderator is to slow down neutrons, and this will make fission more efficient. So thank you so much. These were all my question. If you have any query, any suggestion, you can write in the chat box. You can anytime write me on my mail, that is Jyoti JYOTI 2121 at the rate ISER IISERB at the rate dot AC dot in. So you can suggest me if you have any query. You can write in the chat box, and that's all. Thank you. We will meet again on Monday from 6 to 8 with microbiology, I think, because environmental chemistry has been finished. So we will come up with the questions on microbiology. I think that would be more interesting to like to teach and to learn, right? So thank you so much. Thank you so much for everyone. Now you can leave and have a great dinner and have a good night. Thank you. Thank you so much. Now you people can leave. Good night. Thank you, Sonia. So I think